recording. Okay, cool. So, pretty much, I have some really old block diagrams. I'm gonna try and like update them, and then as I update them, I will explain it to you. So it's not gonna be like a super kind of official video, but as I'm explaining things, it might actually make more sense. Feel free to ask any questions that you have. Um,
Okay.
I'd rather have this be an interactive thing rather than just me explaining and you just listening. So this is the Center
Um,
Console project. So as you can
Actually,
see
for
that,
Center Console, I read through it and I think I understand most of it. Do you think I could have a go at explaining what I think it does, and then you tell me if I'm right or wrong?
oh yeah, of course, go for it.
Just like sort of at an overall level. So from my perspective, reading through it, it seems like the most important part is the power FSM and the drive FSM.
Yeah,
So the power FSM manages between the power states off, main, aux, fault, and transitioning.
yeah,
So it goes into the transitioning state when it's transitioning between states. Otherwise, it goes into while it's in transitioning,
hmm
it triggers the FSMs for like those sequences to power to switch to like main power or to switch to aux power or to switch off.
yeah,
And then it handles those transitions. And then for the drive FSM, it handles switching between drive states, and it also has like the transitioning. So to go from drive to reverse, you first have to go to transitioning and then to reverse, so it can go back to drive if the transition fails.
yeah,
So between all of those, the pedal monitor module just uses pedal RX to like update the pedal state, RXing from the pedal, or that's talking over CAN to the pedal. The button press module just sort of gathers the GPIO interrupts from the buttons and then raises events depending on what button is pressed.
hmm
I'll skip over the sequence FSMs. The e-brake manages the e-brake state, so it gets, I don't know, I guess summing it up isn't that complicated. It just stores the state and then sends. Oh, maybe I didn't read this part that clearly.
No, you're right. You're right. Yeah, it is supposed
Okay.
to be pretty simple. The only part is like I don't mean for this. Like this. There's 40 lines for just setting an e-brake state, and unfortunately, that's just because I think I may have been overthinking this a little bit. I just wanted to make sure that the e-brake messages definitely get sent. So, which
Oh,
is
right, with
why
the retry wrapper. That's
yeah, which
Okay.
is why I'm basically having this CanTX retry wrapper like module that I wrote that basically retries a CAN message a bunch of times, and then it takes like like a success event and a fail event, and then if that message gets acked by all the devices that have been meaning like that were supposed to ack it, then it'll raise a success event. Otherwise, it won't. That's pretty much
Right.
all it does. And
Okay.
same goes for drive output. I think I have a drive,
MCI output, right?
yeah, MCI output, yeah. So when I'm basically like, let's say we want to put the MCI into drive state, and that message gets dropped. Well, we need to make sure that we are in the drive state. Otherwise, we can't tell the rest of the car to be in drive state. So what we do is that we basically just retry it over here, and once this succeeds, we know for sure that it has succeeded because we receive an acknowledgement from the receiver. The receiver being the motor controller, right?
Right.
And it has like a max number of retries. I think that's just an input that you pass in. I think it should be like one of these things. But yeah, these are like MCI output and eBrake TX are almost identical in a sense
Okay.
that they just retry a message a bunch of times and they will raise a success event or a fail event depending on how that goes. And that's it.
Okay.
Yeah.
Writing that
So
down.
yeah, you got all of it right.
Okay.
Yeah, that's amazing. I'm glad that it was easy enough to understand. But a couple things that I wanted to basically mention for power main sequence, power aux sequence, and power off sequence. These are
Yeah.
basically like upon a first glance, it seems like so many things could fail here because and like at every single step of this sequence, something could fail. At every step of the main sequence, something could fail. But I think we want to make our fault handling fairly simple, and especially the faults that happen when we are transitioning from one state to another. I don't really think that's something that's supposed to happen often. Long as we have something to do when that happens, then that's good. Long as we have some very, very easy method of recovery from that state.
Yeah, I agree. I think the way you implemented it was good.
Okay.
Where you request an ACK from whatever is should be turning on at that moment, and then fault if you don't get that ACK. I think that's a good way to do it.
Yeah,
it's reasonably simple.
Pretty much, yeah. I think it's pretty simple too. I mean, when I was looking at the old car's code, they were handling it a little bit differently. This way, I think things are a little bit more clear. You exactly know what happens when the car's turning on or off. In the last car,
it was definitely well defined out. I remember specifically trying to turn on the MS-12 and then sitting down and trying to listen to how many clicks were going off from the relays to try and figure out where I was faulting by counting the number of relay clicks you heard. So
yeah.
This is a step up for sure.
Okay, good. I'm glad to hear that, and I hope that it actually, when we finish it and start testing it, it is fairly easier to test as well. So basically, let's go over all of these sequences. So power aux sequence, main sequence, and off sequence are basically the sequences that they're basically state machines that have pretty much a whole bunch of consecutive states. And once a state basically passes, it goes to the next state. And if at any point it faults, it goes to a fault state, and then it will clear that fault by just raising that fault state, and then it will go back to the none state, right? So these sequences are sequences that get kind of kicked off, and then they go until the end, and then they go back to the none state, right? And if they fault at any point, they will basically reset themselves back to the none state, right? So if you want to basically go from the off state to main state, you kick off the power main sequence. The power main sequence will go through once fully, and then it will go back to its none state, right? And then your top level power FSM will have transition because it will know that the sequence has been completed, right? Which is why I've called them a sequence. They're not really FSMs. They're basically a sequence. And I think in the last card, there was a sequencer module that was doing something like that. But I thought making it a state machine will make it much more clear. So in this block diagram, I pretty much have, there's a charging sequence and an emergency sequence, but I figured out that those are not really needed. So we pretty much have power off, power on. This power on is actually power main because we are on the main battery. And then we also have power aux sequence. So aux. And then we also have drive FSM. I think we have button press, and then we have over here e-brake, TX, and I think MCI output. What else do we have here that is probably a major thing? Oh yeah, I think we need to move all of this to the right a little bit, and then I will need to add main event generator, which is the next thing that I want to talk about. Main event generator.
Alright, I have that in my notes. I forgot to.
Oh yeah, no worries.
But wait, so basically that gets the press events from the GPIO events, and then generates power or drive FSM events. So depending on the button, it'll generate a power event or generate a drive event to move those switch state machines.
Pretty much, yeah. That's exactly what it is. So there's a button press. Let's just keep it down here. And then we also have pedal monitor. And then we also have fault monitor. And we have charging monitor, I think. Yeah, charging manager.
And speed monitor.
And speed monitor, yeah. So I think all of these monitor thingies, if we just put them next to each other, that'd be nice because that's essentially what they do. So, okay, cool. So pretty much you can divide all of this kind of the functionality of Center Console to three things. One is managing the power states, one is managing the drive states, and then one is the basically choosing when to, all of these stuff are for when, under which conditions we decide to, for example, enable a drive transition to happen or a power transition to happen, right? So basically what happens is that when you want to turn on the car, for example, there are certain conditions that have to be met for you to be able to power on the car. So and that all of those basically go here. But let me start by just a really brief overview of how Power FSM works. So basically, Power FSM is the power state of the car. These sequence FSMs are meant to be run only once to make the transition happen. So power main, you run this sequence once whenever you want to put the car in the main state. Power off is basically you run it once to be able to put the car, basically turn the car off. Power aux, you run it once to put the car in the aux battery. And then Power FSM is the one that basically kicks off these guys, right? And in these guys, whenever you have a transition fault, let's say in Power Main, you basically have to send a whole bunch of messages to a whole bunch of people. And one of those messages, let's say it doesn't get acknowledged. And that's the only way this Power Main sequence FSM can fault, is that if a message doesn't get acknowledged. Or it can get acknowledged with an invalid status. Let's say you want to, for example, check the DC-DC status, and the DC-DC status is not what you want. That board can still acknowledge your message, meaning that you will receive an acknowledged message, but the status of that acknowledgement is going to be invalid, meaning that, hey, I'm not in the state that I want to be, right?
Yep.
So if any of these guys fail, that's a transition fault, right? Meaning that, let's say you wanted to turn on the car, but you couldn't, right? Well, how do we recover from this fault? We just want to let the driver know that something like this happened, right? In which case we just broadcast something like that. But then what we can do for clearing from that fault is for this sequence to go back to its initial state, and for Power FSM to remain in the last state that it was previously at, right? Because that transition didn't fully occur, right? And let's say we're like driving the car and we basically like want to turn, let's say we're not driving the car yet. Let's say the car is turned off and we turn it on and something goes wrong, right? We want to be able to see a message of like what went wrong, but after that it's done. You know, like to turn on the car again, we can just press the power again, right? Or we figure out whatever the problem was and we press power again. Maybe it was something that a message got dropped, or you know, a connection was loose, and then we like check up the car and then we press the power again. That should do it, right? So the same kind of strategy for recovering from faults applies to powering off the car and powering the car onto the aux state, right? So let's say you want to, for example, the car is turned on, it's in, for example, drive state, and you put it into parking, and then you want to turn it off. You basically just like press the power button, right? But the car cannot fully turn off. Let's say the power distribution board doesn't respond, or it responds with some like weird error that it has. Well, the car remains on, but then you can look what the problem was with that thing, and then you can just proceed with turning the car off again, right? I don't think putting the logic of the car constantly trying to figure out what went wrong and like trying to clear that fault from itself and retry turning off, I don't think that is needed or necessary, especially for something like that, because these are exceptional cases anyways. If we require the driver to press a button again or like do something again to clear a fault, I think that's reasonable.
I agree.
Right? And on the bright side, that will make this design really simple. You know, there's one sequence that you run when you want to turn on the car, and if anything goes wrong, you just go back, right? There's no other branches of execution that might happen that you would have to think about as the designer. And that was the biggest problem that I had when I was kind of like going through with the design of this, because so many things could fall from so many places. I didn't really know how to clear from all that fault, and all of a sudden the design just gets too messy for you to be able to think about all the corner cases, which is why I think it makes sense to just fail early and fail in a really simple manner such that it's not catastrophic, and that's it. So that is pretty much with the power states. Same thing applies to drive FSM. So if you just read the FSM code, you can pretty much figure out what the drive states are. It's pretty much similar to how a car works. You can take a look at the test files to see exactly what happens. There are two modules that it uses. Drive FSM uses the MCI output module to basically, I think there's a pre-charge module too, isn't it? Yeah,
right,
there's a pre-charge monitor. Yeah, there's a pre-charge monitor as well. Okay, so basically what these modules do is that I think in Drive FSM, when you're in parking, whenever you go from parking to neutral, this pre-charge happens and then you can go to neutral. So what pre-charge monitor does is that it basically sends a pre-charge message to MCI, and then once the pre-charge has been completed, MCI will send back a message. So this guy will wait for that message to arrive, and it will raise an event so that Drive FSM knows that pre-charge has completed, and then it can go to the neutral state. And when at neutral state, we already know that pre-charge has been completed. So if you want to go to drive state, you just basically have to just use MCI output to tell the motor control interface that we are in the drive state. And then after that, you are in the drive state, right?
Yep.
The only thing is that we have an eBrake TX module here, and that is when you want to go to parking, right? You basically have to discharge pre-charge and you have to engage the eBrake, right? And that is basically something that we might have to remove from the car because I think there were kind of safety concerns with having an eBrake in the car. But I left the module there. Modifying this device FSM to ignore the eBrake is fairly easy. And in that case, we would not really have a parking state. So you would only have neutral, drive, and reverse. And your parking state would be basically when you're in neutral and the handbrake is applied. Kind of like a manual car. So that's pretty much as far as this drive FSM goes. Note that within the similar to how power transitions could fault, drive state transitions could also fault as well. And the fault recovery method is exactly the same as power FSM. So let's say you're in reverse and you want to go to drive, some message doesn't get acknowledged. And the only case that it could not work is that if MCI output tries to tell MCI to switch to drive, but that message doesn't get acknowledged, right? For whatever reason. That is a case where that message didn't get acknowledged, so we have an error. But the way we recover is that we remain in the drive reverse state, and we just basically broadcast that fault, and that's it, right? So power FSM and drive FSM are mainly handling transitions. This is for power transitions. This is for drive transitions. Pretty much the conditions, the logic with regards to the conditions under which you do a power transition do not reside here. This is only like when, for example, you want to power on the car, this guy doesn't care if the, for example, pedal has been pressed yet, right? That logic is handled elsewhere. Whenever this guy gets an input, you can be sure that the rest, like all of the conditions for powering on the car have already been met, right?
Okay.
So this part is where we basically check for those conditions. For example, if the car is turned off and the user presses the drive button, you cannot kick off the drive FSM state machine to change it to a drive state, right? Because the car's turned off yet, right? So that's where this main event generator comes in. The main form of input on center console is this button press module, right? The user pretty much, the only way that the outside world can tell this board something to do is via these button presses. I mean, yes, we can receive CAN messages, but this is not really a slave board. This is just like a point where the user interacts with the car. So this module doesn't really receive anything as input. As like a command input, not as a data input, it will receive something, sorry. But as a command input, it will not, right?
Okay.
So This is so the button press has the drive button, the reverse button, the power button, and I think some other buttons too. I think even the hazard button is here, so you might have to actually add that functionality yourself. But
Okay.
basically, what happens? That's just like one really simple CAN message you have to send out.
Yeah.
But basically, what happens here is that the button presses will come as an input, and this main event generator. Sorry, let me just. Our dishwasher makes a lot of noise when it's done. Um, so when this main event generator is, this main event generator will take a look at the state of each one of these guys, and based on these states, it will decide what to do next, right? And if you take a look at the code, I mean, I can probably write a documentation, or even you can write the documentation yourself, but I think the code should be pretty easy. Easy enough
Yeah, I didn't find it
documentation.
hard to
And I
follow.
think, yeah, if it's not hard to follow, then, like, you should, I think, a lot of people think that we should have a lot of documentation, but I don't think that having a lot of documentation, especially in firmware, makes a lot of sense because things keep changing and there's a lot of times that your documentation will not be as up to date with the code. And I think
Yes, it's
the code should
very
be
true.
readable enough that should act as a documentation for itself. So, and
Yep.
that is the single source of truth because whatever you have that executes is whatever you have. And if that is readable, then amazing because you already can look at your code and figure out what it's doing. And that's basically the main thing that I was kind of going for here. And pretty much, if you take a look at the main event generator, you can also take a look at the tests to see what's happening. But basically, for example, for powering on the car, right? For powering on the car, you can basically figure out that it depends on the power state, the pedal state, and the drive state, and that's it, right? So if the power state is off, we basically decide if pedal is pressed, we turn on main, or if the pedal is released, we turn on aux, right?
Yep.
And that's the only event that we raise. If we are in the aux battery, if the pedal is still pressed, we will put the car in the main battery. If the pedal is not pressed, then we put it in off because you can technically turn on from the aux battery to the main battery. And that's just like a feature that they wanted. But if we don't really want to do that, we can just change this one line to turn off the car no matter what. But I think Micah Black wanted a transition from the aux battery to main battery when the car is turned on, which makes sense. And then if the power state is main, meaning that if the car is turned on, we only turn off the car if we are in neutral or parking. So if we are in drive, you can't really turn off the car. See? So like this is fairly readable. I mean, I don't really think, I wrote this code, so I'm definitely biased. But if you think that
No, but I agree for sure. I was initially intimidated by the volume, but I didn't have any trouble getting through it.
So. Yeah, okay, great. Because that's pretty much like what I was going for. And yeah, I think from now on, if you wanted to debug something, hopefully this will help you.
Yeah, I don't think I would struggle.
Okay, great. But in general, the kind of like the main advice that I have for you as the kind of like the new firmware lead, try and make things kind of simple and easy to debug. With
or at least aspire to, yeah.
Yeah, I think I kind of used other people's code and my own kind of like just sitting down and thinking and drawing diagrams and trying to make things simple. These are really your only tools for making things simple. Also, definitely go out and like talk to other people. Come out to me and like talk to me if you have a design and like maybe I can if I have any kind of input I can like help you. But in the end of the day, you are the one who's writing it, and you will be probably the one who runs it and make sure that it works correctly. So it's a matter of like not shooting yourself in the foot.
Yes.
But you will be fine. I mean, this is kind of like the main part of kind of like the power transitions and drive states that I had a lot of problem with. But in the end, it didn't like this was the solution and it doesn't really look that bad. I hope that when we run it, it's not that bad. I've written tests and the tests work. So I hope that past that point, if we are actually trying it out, it will work. So yeah, pretty much the main event generator looks at all of these different states and it'll do stuff. Our charging manager has an empty body right now. It will always say that we're not charging. But basically, this is the guy that also handles the permission. So you were working on the charging previously. Yeah. So yeah, this is where the permission resolver would come into. So the charging manager would have to take a look at the state of the car and see whether it can permission for charging or not. And I think, and you can just take a look at what are the states that you would care about. I think one of the states that would make sense is the car shouldn't be in drive or reverse for us to be in charging.
Yeah.
Right.
Yeah.
I think the main event generator already handles this, where if we are charging, you cannot go to drive. So.
Oh, okay.
Yeah. Process drive reverse event.
Charging state. I see.
Yeah. So if the charging state is charging, we just ignore this drive or reverse button. Right. So these are some, this file pretty much is the documentation. It's pretty much, all of it is pretty much if statements. And this is pretty much where most of center console and therefore most of, the car's behavior comes out. The rest of the files are basically just, slaves and doing things.
Handling the details. Yep.
Yeah. And that's it, pretty much. I think this is center console the center console firmware, pretty much. Nothing much more that comes to mind when I think about this. You also have a fault monitor, because in case the car has a fault, let's say the battery has a fault.
And BPS heartbeat stops and fault monitor triggers.
Yeah, pretty much. So one thing that I did right now is that so with the rest of the faults that the car can have, so there are two kinds of faults. There's the transition faults that could happen here, right? Which are not important. By not important, I mean you can just, in these state machines, you can basically just go back to wherever they were, and that's it, right?
Yep.
And there are faults that are more important, and that is, for example, if the battery faults, right? If the battery faults, you want to disconnect the relays, right? But I didn't really want to put all of that information over here, because this is center console. I think if battery faults, battery should disconnect itself right away, right? And then it will let the rest of the car know that I have faulted, but that's it. I don't think center console should be a proxy for whatever fault handling message that needs to be sent out. If you're in because there's two different pathways. Let's say the motor controller interface faults halfway through driving and the battery's fine, right? If motor controller interface faults, we probably want to disconnect the battery just for safety. I don't know. I mean, we might not even need to disconnect it, but I think it would be safe to just disconnect it, right? So how do we disconnect the battery? Do we tell center console and center console tells the battery, or can we just tell the battery directly? I think telling the battery directly would be better, because here it just has to go through center console. Yeah, it is faster, and it's also less coding, really. Because in that case, center console is merely just bypassing a message.
Right.
Right. So not bypassing, it's passing a message through. So I think if we fault in a more major fault, which is basically like a battery fault, or if a motor control interface fault, this fault monitor should just keep track of that. And the way that the last car did, and I think it's a really good way, is that battery, and also in this car, I think MCI should do that as well. Battery would constantly broadcast its own status, right? So this guy, a whole bunch of boards would always know about the status of the battery. And I think in this car, we should do that as well. So battery can have battery heartbeat, in which in that message, it will have a bit set, and each bit corresponds to one specific kind of fault that could potentially happen, right? So over voltage, under voltage, temperature, AFEs, if one of the AFEs faults, or anything else, right? And that guy will basically set that one bit, and it will send it. And this fault monitor, what it does is that it constantly checks for the battery heartbeat messages, And if the heartbeat is okay, it will clear its own faults if it previously had any faults. But if anything is not okay, it will set its own status as the fact that we have faulted, right? And why is that important? It's because I think it makes sense for now, unless we run into some case where we need something else. It makes sense for now to disable the buttons on the car if we have a fault. So this main event generator will basically not do anything if we have a fault. And this entire board will wait for the faults to be cleared. And how do the faults clear? This fault monitor will clear the faults because it will receive a heartbeat message of that fault that has been cleared. Right? So there's two cases where we can fault. There's the battery, if the battery faults. If the battery faults, this fault monitor will raise a fault. This guy will get disabled until battery figures out that fault has been cleared or it's okay now. In which case it will, respond with like my status is okay, or basically just sending out a BPS heartbeat with no faults. Or MCI has a fault. Let's say it overheats and then it cools down later. It will send out a heartbeat message saying that I'm okay. And then this fault monitor will clear and the rest of center console is good to go, right?
Yep.
So I think that way it puts this firmware into a state where it can, continuously be run, and at no point do we need to really repower this to make sure that things are happening correctly. So yeah, that's pretty much center console. Okay. If you have any specific questions with regards to anything, I think as far as I could, I kind of tried to handle all the possible fault scenarios that could happen. Other stuff could come up, but I think in this kind of structure, if there's something new, I think there's a good place for it to go in this kind of structure.
Yeah.
So,
one thing that is not like directly related to center console, but I'm not super sure about, what are the capabilities of the car in aux main versus off? So
I think it's pretty much driving.
Okay.
Yeah, so you will not be able to use the motor controllers when you're in aux. But that's it. That's the main difference. Unless we really want to, use some power saving.
Or still powered.
Yeah, but I mean, when the car is on aux, that is a form of the car being turned on. So I don't really see a reason for us to try and save any power. Like if you want to save power, just turn off the car.
Okay.
Right.
Yeah.
And in the power off, we should try and keep as many boards as possible off. But in the power aux, I think we should pretty much enable everything, other than the fact that we will not be able to drive, and that's it.
Yeah. So, like when this car is just sitting there, center console is powered by the aux. Is that correct?
Yeah.
Okay. Yeah, that's what I was just a little bit unclear of, because there's like the difference between power off and aux. But powered off is most boards off, just center console on.
Yeah. Yeah, exactly. Well, in power off, most boards are off and center console is on. In power aux, all of the boards are on. It's kind of like putting your car in the battery. Hello? I don't know why, but I can't hear you. Hey, I think my internet cut.
Okay, no worries.
So yeah, you're right. Basically, the way I like to think about it is when the car is in aux, it's kind of like putting your normal car in battery mode.
I'm not super familiar with what that means. I
Oh, so
haven't
when
driven
you
a
turn
lot,
on the
but
car, but not really, like you don't turn on the engine, but you still want to
yeah,
listen to the
yeah,
radio, so you can like, turn the car on, but you can still listen to the music if there's like a center console, you can play around with it, but
yeah.
you're not able to, run the car. This is
Okay, so
exactly
that's
like
battery
that.
mode. Okay, yeah, I think I get it.
Yeah.
Yeah. Okay.
So
Yeah, that's the only question I had.
that's pretty much it. And the rest of these stuff are too old. I don't think they're really relevant anymore. This is pretty much the main block diagram right now that is super relevant. I think I can probably draw out, like have another slide for this power FSM and the drive FSM, but I think most of it should be clear. And if you take a look at the module itself, you can pretty much draw that state diagram yourself. Um,
Yeah.
it's fairly simple. I think it should be easy to understand. Okay, cool. So that's for center console, and that's basically what I mainly was involved with, as well as basically being involved with like making sure that the rest of the car is being designed and like
Yeah.
developed.
Yeah.
But the code that I wrote myself was that.
Okay.
And I'm sure like as you work around and stuff, you might find a lot of problems with my code even. It's okay. Nobody's perfect.
Yeah, you
Um,
never know what comes up.
yeah, you never
We'll
know
see.
what comes up, but I hope that it doesn't cause you too much headache. And if it does, definitely come back to me because I'm not going to be away. Um,
Okay.
what else can I talk to you about? Oh, yeah. Okay, let's go over our build system. Honestly, I think the best way to learn our build system, and I haven't done this myself, I probably might do it at some point because I think it's really interesting the way we build our code. Um, I'm just gonna deep dive into our build system a little bit, but pretty much,
Oh, by
the
the way, you
best.
stopped screen sharing.
Oh, I stopped screen sharing. Oh yeah, you're
Yeah.
right. Let me
Okay.
get back here and share the screen again. Desktop 2. Yeah, there we go. All right, cool. So basically, oh, by the way, this meeting might be over soon because we're nearing the 40-minute cutoff. Okay, so what was I gonna do? Oh yeah, our build system. So pretty much every command that you run, pretty much gets handled by this make file. But it's not only this file. There's basically a folder called make, and all of these stuff are here as well, right? There's new target, git fetch, filter, build test, and then there's the make file. And these are all the stuff that happen. If you want to learn how make works, basically the GNU Make, their official website is a pretty good resource. So GNU Make, yeah, there we go. And it has a manual. If you just read the manual, oh yeah, there you go. And it's available in last updated January 19, 2020. Like it's super,
Oh, okay.
as sketchy as this website looks, but this website is actually super up to date, and it's actually a pretty cool place. It's the GNU operating system, which is pretty much, I think, it's by the Free Software Foundation. Richard Stallman is probably the guy that's in charge of all of this. But they're basically a software cult kind of,
Okay.
where they believe that you should not be able to you cannot use software for commercial purposes. So they're really against Steve Jobs or like anyone else who kind of like makes software that is not free. And if you use any of these tools, they have the GNU license, meaning that you should make that tool open source again. And there are some strict kind of what's it called, strict rules as in that like you cannot use it for any purpose, and if you use it, you have to make sure that it's free and it's open source. But anyways, that's a little kind of like side story. But you can pretty much take a look at the HTML version. I usually just like take a look at it here. This is probably the best, and this is the best kind of source that you can find for figuring out how GNU Make works. Definitely use this as a reference. Don't read all of it. It's really annoying. But I would say it actually has a pretty cool structure where the beginning, the first couple parts of every single chapter are relevant if you wanna use it as a generic user. So I would say going over all of these, but like the first couple parts, and then the later sections in each chapter really get in depth that are basically super super specific, and you probably won't need them. But basically, the way it works is that you determine a target. So like let's say Pylant here is a target. So this is called a target, and then you have colon, and then after that target you have all the dependencies on that target. So right now this target doesn't really have any dependencies. For example, test format has a target that has format as a dependency, and format itself is another target that is defined, right? And that's how Make pretty much resolves the dependencies. You basically have a task, and then you have a whole bunch of other tasks. And these tasks, and they're all called targets, by the way. You have a target, you have a whole bunch of other targets listed out. So Make sure that these targets are executed first before this target gets executed. And then after, pretty much the syntax goes like this. You have the target, colon, dependent targets, and then you have a whole bunch of bash scripts. Or whatever, this is basically bash. Whatever you write here is exactly like bash. And these are called the recipes. So that's pretty much how that works. And you see all of these phony statements here. That's because if a target name usually corresponds to the same file name that target pretty much generates. If a target doesn't correspond to a file, so if you have, for example, like a target here called dirs, right? And it's not a phony target. That's because you have there's a variable probably called here like directories, and it's basically the build directory, bin directory, static lib directory, and obj cache. These are all just directory names. If you take a look at them, they're all defined up here, right? And after the build has been completed, you can exactly see that it basically follows the same structure. So for example, your bin directory is your build directory, which is in build. So it's here, up here. Build, bin, and then after that you see the platform, and then you can see all the stuff that have been created, right? And that this is me after like running the build once. By the way, this build is where the output of the projects go, like after they've been compiled and run. So this isn't our git ignore, which is why they're kind of grayed out here, because my IDE can read the git ignore file. Pretty much this is where we defined all of these rules that we have, where we can do stuff like make format, make GDB, make new, make program. We even have make run. Is make run here? Oh, interesting. We don't have make run documented here. But make run basically just you can run the project. You've done it. Yeah. So this is pretty much how all of those make stuff work. If you take a look at new, it basically runs a Python script that creates the new project stuff. If you take a look at the Python script called new target, you can see what that Python script does, which is fairly simple. It basically just creates these for a new project, right?
Okay.
So I don't know what this git fetch does. Unpack, blah, 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 source.
Is that for Travis?
It could be potentially for Travis, yeah. Yeah. Let's see. Actually, we can take a look at that. Travis.yml. This is our the file that pretty much sets up our build system. And this is basically what runs every time that we commit to our project.
Okay.
I remember we had some problems with this. This Travis.yml file has changed from the last firmware project a little bit because we had some issues with running continuous integration, but everything works now.
Okay.
Yeah, pretty much. If you read these scripts, they're basically just installing the ARM GCC. Yeah, these are the stuff that gets installed. And then after that, we just run all of these commands, which are the same build commands that we ran ourselves. Okay. Right? So everything makes sense so far?
Yeah.
All right, cool. And then if you want to deep dive and understand how our make files, this is basically just our make file on steroids. So it's basically, there's this make file called filter it defines some functions that basically can filter out some stuff. So for example, if you want to, if you pass in a project name that doesn't exist, it can search it here and say missing project or library name, right? Or if you pass in like an invalid platform, it'll, give you all the good messages. That's what this filter file pretty much does. It basically parses the inputs that you've passed into Make and make sure that the inputs make sense. There's the build.mk, which is where we mainly build all of our stuff. And pretty much you have the target, and the target type can change, and depending on your target you can choose different compilers. And we only have two targets right now. One is Linux and one is ARM-GCC. And for that, I think, what is the there's the build test too. Okay. So I think this, I remember reading this before. Oh yeah, by the way, this is basically like how you have the application target. So this is within the bin directory. So you can basically define, like you can use your variables that you've defined as a target name here. Make allows for that. And you pretty much call dep to lib, so it basically looks up all the libraries that are required for that thing. And then this OR operator, I don't know what that does exactly. But all of these stuff makes sense if you look them up on the internet. Like, what does this mean in like Make? But each $sign and then you do something like this, it pretty much concatenates some stuff. I remember like looking at it once. You don't really have to understand how this thing entirely works. To be fair,
but I still have like a better idea now that you've gone over it a little bit.
Yeah, I just wanted to make sure that you know where all of these stuff come from. They're not set in stone, or they're not God given. We had like someone has written these, and I think the main person was Calder, and Calder has written all of this stuff. And to be fair, like every time I ran into some problem, I was able to figure it out by myself by just like going through these files. So I don't think you would have any problems. And then. But if you understand this file completely, that would be amazing, because then you can, restructure this project to add some new features. And some of those features that I would really like to see are, for example, having test projects and having our test projects be separate from our main projects, right?
Right.
Because right now, if we have a test project, we just prefix it with test. Whereas if we have the test projects, we can, do much more cool stuff with them. You can have a test project, and you can bring some other scripts in where you can mock out some other parts, and then do all sorts of cool stuff with it. So understanding these make files would definitely help you, but they're not necessary. We can go to race with someone not really knowing how this works. But knowing where it comes from is probably necessary as a firmware lead, which is why I wanted you to go through them and understand how they work. Let's see. And then we have platform. For a platform, we have x86, and then we have the STM32. This platform.mk, oh yeah, there we go. This platform.mk is where we define all of our compiler-specific stuff. So if you take a look at this for the STM32, this is ARM non-EABI GCC. So this is an actual like command that you can run in your Vagrant. If you like set up Vagrant and like go in it, you run this. This is the GCC compiler for ARM. So yeah, you have your compiler, you have your linker. This LD is the linker. You have obj-copy and obj-dump, which are two utilities that compilers usually use after they generate an object file. And then you have sides for figuring out, I don't know what that exactly is for. I don't even know where it gets used. Let's see. Oh, apparently it doesn't even get used. Even this obj-copy or obj-dump don't really get used. I think these are just like everything that a toolchain usually has, but they're not really getting used here. I think only CC gets used here at some point. Yeah, but you can search them to see where these exactly get used. But yeah, you have your compiler, you have linker, you have obj-copy, obj-dump, size, AR, and you have OpenOCD and GDB. OpenOCD is the thing that we use to be able to program our. It's basically like an unchipped debugger. It's a project that was written that allows you to pretty much run code on the STMs and be able to debug them, or like run GDB on them and all that kinds of stuff.
Okay.
This is the OpenOCD command that we run. So if you run this in your command line, this is basically the same as running make program. But as you can see, there's a lot of configurations that the make pretty much hides out from you. This probe is the probe that you use. So we have kimsysdap, and then we have ST-Link v2. ST-Link v2 is the one that comes with the default by the STM. This is basically that USB connect. Have you ever worked with the discovery boards?
I haven't.
You haven't, okay. So the discovery boards are basically our same STM32 microcontrollers, but they're basically exposing all of the pinouts so that you can basically just play around with them. It's kind of like an Arduino, but our STMs, but for our STMs. Right? So we used those development boards initially to be able to figure out all of the capabilities of these chips, and also being able to write drivers for them and libraries and all that kinds of stuff, right? Which is why you have that probe option here too, because probably when they were developing it, you can basically still run the same code on those boards using the different programmer. But yeah, that's all it is. And then here's the target for program. This is pretty much what it does, OpenOCD, and then it passes all the config files, and then it passes the target binary. So after the target binary has been generated, it'll pass it here to OpenOCD. GDB pretty much opens a GDB session where you can, step through your code, which is pretty cool. I definitely recommend doing that. We have what? Sorry. Yeah, that's a really cool thing. It's kind of hard to get used to, but if you get used to it, it's gonna make your life a lot easier. And it helps you understand things way better, because like once I wanted to just go over our GPIO library and just read the data sheet and be able to just write the driver myself, as opposed to using whatever we currently have. And GDB will help me a lot over there, because in GDB you can do really cool stuff, such as you can like pretty much read, like as the application is running, you can read any place on the memory, like what the value it is. And you can also write to any place on the memory. So I was able to like manually make a LED blink by just writing to this register that was mapped to my memory. And that was pretty cool to me, because I was like, holy shit. Because like that's what driver writing is. Like if you take a look at our drivers, they're all basically just calling these functions that have been generated by STM, that under the hood, they basically just write zeros and ones into a whole bunch of registers. That's how you interact with the, with the chip. And that's the only means of interaction that you have, because it's a digital chip. So that's a really cool thing to think about. And that's, it's very simple in terms of the concept. And it's very complex if you just start reading the data sheet. But at least knowing where things come from helps you a lot. But honestly, like all of this sounds like a lot, but at the same time, it's not that much. It's easy to understand. It's something that you can start off of, and then when you read a data sheet or something, you're not going to be lost. Hopefully.
Yeah, at a high level. Yeah,
on a really
just
high level.
Getting through all the details takes a while.
Yeah. And that's pretty much it. That's pretty much what the platform that MK works for, or does for STM32. Same thing exists for Linux, so you can pretty much see what the stuff are. There's CC, there's LD, object copy, object dump size, AR, GDB. All of the equivalent for Linux pretty much is listed out here.
Okay.
Yeah, that's pretty much it. So this is how our stuff works. If you run code on Linux, it pretty much compiles your code or your application code, and it'll generate an executable on Linux that you can just run. So when you do make run, it pretty much generates that executable and runs it right there.
Right.
And that is it. that's pretty much it. What else do we want to look at? Oh, there's also some other cool stuff that I found out that I think would be useful if you want to take a look at. There's this select programmer file. This is basically just like looks at the USB devices and finds the kimsystat one. So this is how we select the programmer. This is the script that gets run. This is the OpenOCD config file. So this is what the OpenOCD uses to program the STM. So if you take a look, it's pretty cool. This is the function that runs. So you sleep for a little bit and then wait halt 2, I don't know what this means. But then you flash this write image. This is a command. So you basically do flash write image and then erase. And you have this image file, which is the binary file that our build system just generated. And then you write it at 0x080000. So this is where our, I think, flash memory starts on the memory. So if you take a look at the data sheet, this number matches the same number as where our flash memory starts.
Okay.
So yeah, this is basically what we do. We flash it, and then we sleep for a little bit, and then we verify. So we read it back to make sure that it basically wrote the same zeros and ones, right?
Right.
And then you do reset run, which basically what it does is it, I think it just pulls down the reset pin on that board. That makes sure that the board can get repowered and start executing from the first line that it can find from here, right? And then there's an STM erase that basically just mass erases stuff, right? So this is the OpenOCD config file that I thought it was pretty cool. GDB flash. Oh yeah, this is basically just something that GDB uses to flash stuff. Let's see, select programmer. We also saw this. LD scripts. Oh yeah, this is some cool stuff that I found here too. Okay, so this is the linker script for the discovery board. The linker script pretty much defines. This is like super low level in C, by the way. If like these stuff usually come up with like if you have an interview with like what's it called, like NVIDIA. At NVIDIA, one guy was really into compilers and only asked me questions about this.
Okay.
And I couldn't answer the questions at the time, but then after I read this, I was like, oh my god, this makes sense. Anyways, this stuff is, and they won't expect you to be like super low level on this. Like they won't expect you to know everything. But if you understand this file, I will guarantee you that you will like understand most of those questions too, and you will be able to answer them very confidently, which is really cool. But yeah, this is where you define your memory sections, because when you write code, your code must know where the memory exists. And this is what your linker does, because your code pretty much generates an object file, and your object file pretty much like reads and writes from memory, right? Like your code gets compiled down to machine code. But for the address values, you still don't know where the addresses start and end. So all of the addresses that you have in your object file are merely offsets. And then where we define those offsets should start from, that's basically where your linker comes in and makes that happen pretty much. So your linker is where you define your memory. And the flash starts at 8,000 and its length is 128 kilobytes. And that's, kilobits. And that's exactly our STM32s.
Wait, is it not kilobytes?
Actually, it is kilobytes, I think. You're right. We have 128 kilobytes of flash and 16 kilobytes of RAM.
Okay.
Which is a lot, by the way. Like, I don't think any project is going to get bigger than that. Our biggest projects, usually when you program something, it'll tell you like what the size of that project is. And it's very small. It's like ridiculously small. Yeah. And then you can basically start define a whole bunch of cool stuff here too. So you can define your stack size. So you can fix your Stack Overflow issues if your stack size is too small. So and this is where that gets defined. Flash starts is origin flash. I don't really know what this means. Flash page size. That's basically like, I guess if you're accessing your flash memory, what is the page size for that? And by the way, we didn't write this. We probably like grabbed this off of like somewhere else.
Yeah, or
Right.
they probably provided with the board, or
Yeah. They were provided with the board.
Okay.
So don't freak out when you read this. Like no one
Yeah.
read the manual and like read the data sheet and decided to write this. But if you read the data sheet and come read this, it'll all make sense, and it's really cool
Right.
because you finally figure out everything, kind of. This is another linker script that basically includes these other two linker scripts. That's what it does.
Okay.
So this is pretty simple. And this is where I had one of those aha moments where I like really enjoyed it. This is another, so sections flash is another linker script that also gets used in our projects. And if you read it from the top, you can pretty much see it's like sections, and then there's like your ISR vector. So all of your interrupt service routine vectors are defined here, which is really cool. So if an interrupt gets called, it has to call some special function, right? That's what happens when your interrupt gets raised, right?
Huh?
And this is in your linker script where that gets defined. So it says like this address is where I jump to if an interrupt gets called. Well, this is like a couple levels below what we interact with. We just pass in a callback, but basically that callback gets called because this first function up here gets called.
Okay.
And then there's a whole bunch of flash stuff, a bunch of other stuff, initialize data section, data is in the RAM, blah, blah, blah. Here you basically just, like this BSS and BSS start, these stuff, if you like search them, Google them, they will come up. Like there's a lot of nice articles that explain what every single part is, which is really cool. And then, let's see. What was the cool thing that I saw? Data, sections, debug. No, this is not what I was looking for. Let's see. GTB flash. Oh, wow. Where was it? I swear I saw something here that I really liked at some point.
Okay.
Let me search.
Maybe I'll stumble across it eventually. But
yeah, okay. Oh,
I think where I am now, I don't have enough knowledge to understand it, but
it's okay. So I didn't do this to scare you, by the way. Like this is all like you don't need to know all of this to be able to do stuff.
But it is cool.
But it is very cool. Okay, so one really cool thing. So if you ever come across it, oh, entry reset handler. Oh yeah. Okay, there we go. Reset handler. Reset handler. No, it's not here. Okay, so this basically defines an entry. This entry is where like things first start. So like the first part of like the compiler doesn't necessarily jump to main function. It jumps to a different function called the reset handler here, I think.
Okay.
And if I search this here in our project and not necessarily center console, let me see. Okay, reset handler, startup, FSM. Oh yeah, there you go. So you have this entry. Oh yeah, there's this startup script that we use. So startup STM32 F0. Yeah.
And these are the libraries provided by STM, right?
Yeah. These are the libraries that have been provided by them. Okay. So if you, I think one of these, because all of these are basically just like in libraries STM32. So if you take a look at here, there's libraries, and then in libraries we have KimSys, and then we have a whole bunch of stuff that we made, right? This
Uh-huh.
STM32 F0XX. Ooh, what are these? Oh, yeah. Oh, there we go. I found it. Okay, cool. So, um, one really cool thing here is this .s file, and this is the first file that gets run in our
Okay.
projects. And it's really cool because you can see a whole bunch of really special keywords that have been defined over here. Um, so if you take a look at this, if you read this stuff, they have some like interesting information. It says set the initial program counter to reset handler. So this is basically where that reset handler first starts.
Right.
And this is where that function has been defined. This is basically assembly code. This is what it is.
Okay. It's pretty cool that they provide like the commented assembly code.
Yeah, it's ridiculous, man. It's so cool. But basically here what it does is it enables the clock, blah blah blah, and then it copies all of the. So this is basically like what this does: copy data and loop copy data. So it loops and then it tries copying data like by loading it to one register and then writing it to a different memory location. But what this does is that this application starts. I think this is basically like where that thing starts. Yeah. It copies all of the application code from the flash memory to the RAM, and then after everything is done, it calls system init that like enables some clocks, retarget init, blah blah blah, and then it calls main, right?
Yeah.
So this is really cool because your main function is not a special name. You can change this to like caret and it'll run caret.
Oh.
That's really cool. Like I tried this. I literally tried this. I changed this to potato and then I had a potato.c file that got run first. And having a main file doesn't do anything.
That is pretty neat.
Yeah. So this is some cool stuff. And then you can see a whole bunch of like specific interrupt request handlers that have been defined over here. That if you take a look at our code, at the lowest level, we pretty much call these functions or something like that. So yeah, that's the startup script. And then if you were wondering where, like if we like log output something, it goes to UART and not go to, like because for STMs, you don't really have any means of like logging out stuff, right?
Yeah.
So how do we do that? The way we do that is by this retarget C file. And if you read this code, all it means is pretty much we just enable UART and then we retarget all of our printf outputs back to there, pretty much.
Okay, that makes sense.
Yeah, and this is a whole bunch of like section, attribute, ASM, whole bunch of assembly code. This is like as low level as it gets. But if you understand this stuff, it's going to provide you much joy and lots of bragging rights in interviews, which is really good. And this is our retarget configuration file, so you can see the GPIO, TX, and RX. These are the clocks that we enable. Retarget.h, you just call this retarget init, making sure that our I/O, like our standard I/O, is going to UART. And if you read this, this is basically what that does. And if you take a look at this, it says retargets STD.io to UART. So your STD.io will be sent out like that. So you pretty much define what printf does here, really. Wow. Cool stuff. And I don't know how, like, I don't know if someone wrote this and from our last leads. If they wrote it, it's really cool. If they didn't write it, I mean, they probably...
I feel like that's probably STM, right?
Could be STM, but it looks like us. It has ink source, and it much looks like what we would write. And it has a rules.mk file.
Oh, that's true.
Yeah.
Huh.
Yeah, it's interesting. And every rules.mk file lists out the dependencies that project uses. So in this case, this retarget uses the standard per fault drivers. And C flags are like these two C flags that it uses when it's compiling the code. Hello? Yeah. That's pretty much it. So yeah, that was my deep dive into our build system. I hope it was useful. I found it quite interesting, and it teaches you a lot, like a shit ton. Um,
Yeah.
this is probably the result of like years and years of like many embedded systems co-ops that Titus had that are just here.
Okay.
Yeah, so yeah, like I said, this is like first class information that you get to learn as a firmware lead.
Yeah.
But yeah, this is as much as I learned when I was, deep diving into this project. There's still, much to be learned from it. One day I'm thinking of just like rewriting all of the build system myself to understand it
I
fully.
think you'll have time.
If I have time, yeah, because like right now I won't have any time. But you won't need to understand it. If you run into problems, definitely I'm here. We can even reach out to Calder, who is the first person that wrote all of this stuff. Genius guy. He works at Google now. But yeah, that's pretty much it. I hope this was useful.
Yeah, it was.
Yeah, you pretty much
And
know about this car as much as I do now.
okay.
Yeah, so good luck. Is this it, pretty much?
Thanks. Yeah, I think that's all I wanted to ask. And
Okay.
then I guess we'll set up a meeting for going over new member tasks and maybe the Jira.
Yeah. We need to go over the Jira tickets and make sure that they're getting handled too. All right, cool. Awesome.
Okay. Oh, by the way, just really quick, did you work at Sandvine?
I did work at Sandmine, yeah.
Oh, yeah, that's where my co-op is for the next term.
Oh, really? That's an awesome company.
Okay.
Yeah, it's really good.
Any thoughts?
What
or
team are
things
you on?
you think? Embedded software engineering.
Oh, that's good. I was on the cloud services team, and it was a really good team. The company as a whole has like a really good working, like it has a really good work culture. It's kind of startup-y. There will be
Okay.
lots of like food trucks and lots of just fun stuff, and they pay well. And the team
They
that
do.
you're on
It's
is
true.
what? Sorry.
It's true. I was surprised.
Yeah, and the team that you're on is actually a really good team. Like embedded software at Sandvine is usually a really good time because you will be
Okay.
surrounded by people that have been in the industry, and they're really probably the best people at that job because Sandvine really is like one of the top companies in what they do. It's not like Google, but the people that
Yeah,
are
when you
there
see
are
like
definitely
Comcast on
as
the
smart as
customer
people as
list.
in Google.
Yeah.
Yeah, so definitely try and learn as much as you can about C and C++. There's probably some really, really good guys there. And
Okay.
like patents, like engineers that have lots of patents themselves.
Okay. Yeah, they're like NDA and confidentiality was like just as strict as AMD, which was my last co-op.
Oh,
So
nice. Yeah, I worked at Sandvine.
seems
I
good.
kind of wish I worked as a embedded developer there. I don't really like. I mean, web development is fun too, but embedded would have been much more interesting now that I've done all of this stuff.
Right.
But yeah, definitely enjoy it. That's a really good combination to go with Midnight Sun. You can, definitely learn a lot.
Okay.
Yeah, don't burn yourself out, but definitely have
Yep.
as much as fun as you can because these are all really fun stuff.
Okay.
Yeah. All right. Good.
Thanks.
No worries.
Yeah. Talk to you another time.
Yeah. Talk to you another time. I'm gonna end this meeting and end this video recording.
Yep. See ya.
See ya.